be just a little bit of a tour of some work we've been doing on the psychology of uncertainty and information and our forays into how we might try to teach some of these ideas, especially work with primary school children. In the beginning, I'd first of all like to thank very much Gerd and the ABC group for support over many years, the Max Planck Institute, and also, as Laura mentioned, the DFG. So this new Frameworks of Rationality program was really instrumental in getting a lot of the collaborators together. So we got together a few times a year. We'd spend a couple days talking about different ideas, and that's very critical for the development of what I'll present today. Okay, so something I was interested in, I'll just go really quickly here, is partly the idea of what would make an experiment useful, and also the question about whether what maybe normatively, if you will, would make an experiment useful might also be interesting as a model of psychology. And just real quick, of course, there are many different ideas of what would make an experiment useful. One broad way of thinking about it is that a good experiment would somehow discriminate among, say, two or more research hypotheses under consideration. If you just ask someone on the street, you might hear something more like, well, a good experiment would tend to falsify a particular working hypothesis. And over time, these ideas came together in psychology, and I, among many others, have looked at things like which of these ideas are somehow normatively best, and also which best explain people. And a lot of this stuff I'll be talking about today is in the framework of these Bayesian OED, or so-called optimal experimental design models. So several of these are built on some of the information theory ideas like Shannon and Lindley. Okay, so an idea that comes up in a lot of these models is that you might go from a state here at left. Can you see my mouse bouncing around? I tried to illustrate. From a state of high uncertainty, trying to get to a state of certainty. So for instance, if you're playing a kind of guess who or 20 questions game, you might be trying to figure out which of these face cards has been drawn at random. And this idea of entropy, and I'll be a little bit loose today, I'll sometimes say uncertainty, but for today we know what the probabilities are. That this idea of entropy could be a kind of yardstick or measuring device that lets you know how far you have to go. So there might be some cases where there's many possibilities, but one of them is much more plausible than the rest, or there might be cases where there's few possibilities, but they're similarly uncertain. And this idea of entropy basically gives you an even-handed way of quantifying how much do you still have to learn. So if you're playing a game trying to figure out what face it is, you could use that to see how much you have to go from where you are right now towards the idea of hopefully knowing the true state of things, say what face it is for sure. The first real big project that we did together with Laura and friends, so this was Boyan and Divyak's master's thesis, was actually working with this particular game, this Guess Who game of Wer ist das? And we explored it a little bit with fourth grade, so about 9-year-old children. And here the task is you want to figure out which of these faces has been chosen. So there are face cards, and one of them selected at random with equal probability. And the rules are you get to ask yes/no questions about the physical features of the faces to try to figure out which face card's been drawn. And what do people think, first of all, would be a good question to ask here, maybe the best question to try to figure out the face that's been drawn?
Silence in the room. Elizabeth, what would be a good question? Gender.
Gender. So is it a girl, or is it a boy, or something like that? So that's definitely a popular question, right? So for instance, you could ask, is it a boy? And if the answer is no, then you might go on, do they have brown hair? If not, you might go on, do they have glasses? Yes, they do. And then at this point, maybe you ask if they have a hat. If they do, you're done, right? So, yeah. we'll talk about how you might get at that. But before we do that, I'd like to ask a little bit. So our collaborator, now Professor Björn Mader and Ben Klimek, at the time Björn was 34 and Ben was 8. So Björn actually discovered this game and introduced it to us, and we thought it was cool. We should do something with it. But Björn was playing this game with Ben. Ben is the son of some friends. And
No, no,
who
no,
do you
he's his nephew.
Nephew?
Sorry.
Okay. Okay, I thought it was son of friends. Anyways, uh, Björn was introduced to the game by Ben, and who do you think was better at the game? So Björn's a very, very smart guy, Professor Mader. He knows a lot about uh, statistics and theories of cognition. Um, who did better the first time they played? They did it so they played like against each other, and the question is who figured out the face first?
Ben.
Ben,
Given that
thank you,
you
Reza.
ask
Yeah, thank you.
conditional on your question, it must be Ben.
Yeah, okay, very good pragmatic knowledge, Garrett, and thanks, Reza. That's right. So the first time they played, Ben was better, and according to Björn, it went on like this for a period of time. So Björn thought this was very interesting. So he came back to the Max Planck Institute, and we started looking at this. We thought it was interesting. We wondered what might be going on with this game. Why is Ben so good at it? And well, also, what would be a good strategy, period, for the game? And one idea would be exhaustive search. So basically, you think of every possible kind of question tree. Technically, that is optimal for this kind of problem if your goal is to figure it out in the smallest number of queries on average. We don't think it's plausible as a psychological model. Another thing you might do is some kind of stepwise greedy lowercase optimal method, like trying to minimize expected Shannon entropy in the probabilities of the faces that you expect after each question that you ask. Now, Gerd, when I say that, will think that something like that couldn't be plausible as a psychological model. And I'm going to say later on that I think it can be helpful to have a kind of tension between a more kind of mathematical or computational description of things and a more kind of algorithmic description of things. I don't think they're in opposition to each other necessarily. And of course, Ben might have some trick. He might have just memorized what's good. It might be trial and error. Or he might be doing something like this game, this strategy of trying to split things in half as best you can among the remaining items seems to be a reasonable strategy. And so we wondered what Ben was doing. And yeah, others, and we also have noticed that in some cases, so for instance, the version of the game that I described here, you can actually prove that, for instance, the split half strategy will invariably identify the question that has the highest information gain in the next time step. So there's not necessarily opposition between these different ways of thinking about the problem. Now, what if I had shown you this set of faces and asked you what would be the most useful first question? Again, it's the same story. One face has been picked at random, and you're trying to figure out which face it is. And let's suppose your goal is to use a strategy that on average will minimize the mean number of queries that you need to figure it out.
Elizabeth?
Is the eye color red?
Oh, as I heard from Reza, is the eye color red? That's an interesting one. I think that must be in the model. I don't remember offhand how good of a question that was. I think it's not a bad question. Did Elizabeth have an idea as well? I didn't hear.
A beard? The beard question?
A beard? Yeah, so we were doing this in Germany, so it was a Bart question. So goatee or mustache also count as Bart for this.
Bart and Bart. It's not Bart.
Yeah. So for this set of faces, it turns out that at least according to the features that we could identify, you would actually do the best. And we did this via exhaustive search. If you start with the, we call it beard, but Bart question. I suspect that red eyes isn't bad. So why is it that we have a different intuition here than in the first scenario that I illustrated?
Because we cannot use gender.
You're allowed.
You're allowed.
No, but I mean, it doesn't help us. That's what I'm
But
saying.
why
It
doesn't it
doesn't
help you?
divide it by half.
Okay, so if you have some kind of proxy, like let's call it split halfiness of the question, then for this set of environmental probabilities, asking about gender isn't as useful as it was in the previous set. That's right. Okay, so what do you think 9-year-olds in southern Germany did when Bojana asked them this thing? So it was a between subjects manipulation. Some kids got the yellow set of faces and some kids got the blue set of faces. What were the favorite first questions? I won't talk about the rest now. What were the favorite first questions for each set of faces? Okay, I'm gonna move quickly. We've had some audience participation. That's good. Okay, so in the yellow set of faces, the so-called representative environment, we call it representative because we think 9-year-olds in Germany have probably experienced men and women, boys and girls in, say, close to half and half proportions. And the statistics of the cartoon faces there wasn't quite 50-50, but it was close to it. And in that environment, so this is what happened through time, there was a clear preference for the, call it gender question. So either saying, is it a boy, is it a girl, or something like that in the first question. In the non-representative environment, there's a distinct change if you look at these lines. From the representative environment, but it wasn't enough that the beard question, which is theoretically better here, was like distinctly more probable or distinctly more frequently asked, I should say, than the representative environment. So there was some influence, we think, of the environmental statistics. Maybe showing kids the set of faces didn't fully override their experience in life. We don't know. We're continuing to explore that. But we saw that there was some sensitivity to the environmental statistics here. Okay. Okay, now we might ask what's going on there. Okay, so for instance, it could be that kids are using this split half strategy. There's data from other tasks I won't talk about today that suggests that they don't maybe always do the split half strategy. So right now I'm going to ask what kind of information model is compatible with this preference for a split halfy question. Okay? And the models I'm talking about are from this paper. Vincenzo Cruppi was the first author in cognitive science. I'm not going to go through the math in obviously any detail, but the paper is there today. I'm just going to give some kind of highlights. This was another main project that happened as part of the DFG New Frameworks of Rationality project that we did. So what is uncertainty? Okay, this is really entropy. So the idea here in a lot of these theoretical models is that information is reduction in uncertainty. But what is uncertainty in the first place? So one idea would be, say, not knowing for sure. Another would be, say, just count up the possibilities. And that feels very heuristic to me, actually, both of those ideas. Another one would be, well, what's the probability of guessing incorrectly? That feels a little bit less, but still kind of heuristic-y to me. And another idea is that uncertainty is expected surprise. So if we get back to the faces, that would be like if you could just ask God, sort of some oracle, what face is it? And you'd get the correct answer with no kind of noise in the transmission or your perception of it. How surprising on average would it be to you to get the true answer? And it turns out this is one of the things that came out as we explored this mathematically, is that all these more kind of heuristic-y feeling ideas actually can be seen as special cases of this expected surprise idea in this framework. Okay. The notes below I've already talked about. Okay, so I'm not going to go through the math at all today. Okay, it's in the paper, but I just want to highlight where we get to in the end. So the idea in this framework of models is that an experiment, so I call it D, so you can think of that as data, and if it's capital, it's a random variable that corresponds to all the possible outcomes of the experiment, which I do with lowercase d, that an experiment's expected usefulness is the difference between the prior entropy across the probabilities of all the possible states of the world minus what you expect. So this is an average, minus what you expect to be the posterior entropy after you see the results of that experiment. And this idea of information gain is based on that. Usually it's based on Shannon entropy. And what turns out to be the case when we explore this mathematically is that we can get not only Shannon entropy, but many different, we think, interesting entropy and information models from a unified parametric framework. And the key ideas here, so in the vertical axis, which I call degree, it's how do you measure surprise? So for instance, for Shannon entropy, it's the log of the inverse of the probability of the event, and what kind of an average is used. And that's the order parameter. But we've got two parameters, and once you specify those, then you have a specific kind of entropy function. And we can ask, well, what would be compatible, for instance, with a preference for split half questions on the 20 questions game? What would be compatible with what people do on other tasks? And how could we maybe teach about these things? Okay, we know from previous work that it works okay on the 20 questions task, but we know that Shannon entropy, though it has nice theoretical properties, it's not a serious candidate as a general purpose descriptive model of human intuitions about the value of information. So we would like to explore a range of models, say, that could have this preference for split half questions on the 20 questions game. And it turns out there, I've plotted things for various degree parameters. So it turns out, and we show in the paper, that the order parameter doesn't matter for this particular question. It's just the degree parameter. And so we can plot, like here, if the degree parameter is 1, so that's true for Shannon and for all the Renyi entropy and information models. If the degree parameter is 1, you're maximally, you value a query maximally if there's a 50-50 split, so proportion of items with the feature, and it drops off kind of smoothly up to a point where if all the items have the feature or none of the items have the feature, you don't value that at all. If the degree is, if the degree is 1.9, you still prefer 50-50 split items, but not as strongly. If the degree is 0, you also have this preference, but it turns out that if the degree is greater than 2, you actually prefer to just ask, is it that guy, than to do a 50-50 split question. Okay, so these results would suggest that, okay, well, maybe some model with degree up to but not quite 2 would be a reasonable candidate, and we could of course see if something explains people's intuitions across multiple tasks. Okay, so I said, yeah, Shannon is okay for 20 questions tasks, but it doesn't work for some other tasks in the literature. And we've wondered if it might be possible to more directly query people's ideas about entropy or probabilistic uncertainty. And of course, if we might be able to use games, so the 20 questions type games would be one approach, or other games to teach about the math of uncertainty and information. And at this point, I'd like to introduce our entropy mastermind task. So this is based on the classic kind of mastermind task with some tweaks, but the basic idea here, you're trying to figure out now a hidden fruit code. In this example, the code has 3 items, and the thing is that the code's generated, so at the top is a kind of schematic icon array depiction of the fruit bowl. The code's generated by picking items from here with replacement. So in this case, for any individual item, it's a little bit more than 50% chance that it's a pineapple. Okay? And the player's task is to try to figure out what the hidden fruit code is in as few queries as possible. So in their first query, they guessed all pineapples, and the feedback was 2 smiley faces and 1 frowny face. And what that means is that 2 items in the guess were exactly right. 1 item wasn't in the code at all. But importantly, we don't know which 2 items were exactly right. Okay, so the smiley faces always come first. So in the second guess, they did pineapple, pineapple, blueberry, and they got 1 smiley and 2 neutral faces. So this means that 1 of the items in the guess is exactly right. 2 of the items could be right if they moved, and the player has to figure out the position of the items. I think by the time we get here, the player knows that the code, the hidden fruit code is blueberry, pineapple, pineapple. Once they guess that, they get all smileys and they can go on to the next game. We like this game because it's well, it actually turns out to be not just something that's fun for children and adults, but the combinatorics of trying to plan sequentially on this game blow up enormously. So it's actually had, I'd say, at least 100 years of computer scientist time devoted to figuring out what strategies might work. And they're mostly various kinds of heuristic strategies on different variants of the game. And we think it's complex enough that we'll have to take psychological constraints seriously in the modeling. And we want to know if we can use this kind of game to teach mathematical concepts. So for instance, this idea of maximum entropy that Laura mentioned in a gamified, so hopefully intuitive kind of way. We have some early results on this that we think are promising, and Laura Bertram, who will present later, is developing this line of work further. So let's just say I asked you, so there's different kinds of fruit bowls that we could have. And I think you can see for any fruit bowl, we could describe the probability of drawing a pineapple, blueberry, etc. Now, we've got this mathematical model that I introduced of possible ways to talk about entropy. And if I asked you to describe people's intuitions about how hard a fruit bowl would be for this game, if I said, here's the general purpose formula for entropy, and by the way, if it's undefined in your case, don't worry, there's a well-defined limit. Just figure out what the limit is, and then that'll be your formula. If I asked you which order parameter, so we're corresponding to the horizontal axis in this quadrant, I guess we call it, is most psychologically plausible, what would you think? Would you have a real quick idea? Say Shabnam or Reza? So maybe I'll just go ahead here. So I don't find this to be an especially meaningful representation. I'm not saying there might not be a couple mathematicians somewhere that would immediately make sense of this, okay? But I don't find this especially meaningful, okay? But if I told you, okay, here's 4 different fruit bowls, okay, that you could play the game with, okay? And if your goal, so let's say I give you an endowment of 10 stickers and you have to pay me a sticker for every question that you ask, trying to figure out the hidden fruit code. If I ask you now, well, which of these fruit bowls would you prefer to play the game with to try to maximize on average the number of stickers that you get to keep, what would you tell me here? Anybody?
Top left.
Top left? Okay, so that's my intuition, and it seems to be a lot of people's intuitions. And we could go through why we think the ordering should be top left, top right, bottom left, bottom right, in order of increasing difficulty. Okay, but so the idea that's underlying this work is that maybe this gamified means of presenting things might be enough to build an intuitive understanding of some of these ideas about probability and entropy, even with young-ish, say 7 to 9-year-old children, before we would think about probably introducing ideas about probability or information theory explicitly. Okay, so more specifically, we could ask things like, if you consider two fruit bowls, now they're more marble bowls here. At the left, it's half yellow and half blue. On the right, it's 95 blue and one each, black, pink, green, red, and yellow. Are they equivalently hard for purposes of playing the game? Or is one of them easier? Would you do better with it for playing the game? And let's suppose you told me that this case here, so 95, 1, 1, 1, 1, 1, this distribution would be easier for playing the game. Now, what about this case? So now we've got 85, 3, 3, 3, 3, 3 for the probabilities. Is that easier or harder than the 50-50? And basically, we could keep asking you a series of questions like this and try to find a point of sort of psychological equivalence, which for us is a proxy for your understanding of uncertainty or entropy on the task, okay? And as we explored this, it turns out that for this type of problem, depending on, so we could use whatever technique to figure out, say, which of these cases here you feel is equivalent to the 50-50 case at top. But once we figure that out, then we can actually map you theoretically to the horizontal axis of this space here. Okay? So that's one of the things that we're looking at in this work.
Jonathan, you
Yep.
don't have much time
Okay,
left,
we're almost done.
right? Okay.
Okay, perfect. So we're trying to understand which models are most plausible from a kind of descriptive standpoint. And a fun note is that some of these models are more kind of heuristic. So in the beginning, I mentioned you might, for instance, just count the number of possibilities. And we see that in some parts of the space here. And we're currently working, so this is the last slide. Don't worry, Laura. This is the last slide. We are currently working to see whether we can use this game as a tool for teaching. I alluded to this, ideas in information theory and probability. Trying to see if we can make the game adaptive so that it learns about the child or adult's knowledge and state and say gives them tasks that are most helpful for them. And we're trying to understand what happens with children and adults in different kinds of psychological states, which we'll hear about a little bit later from Laura. So thanks very much.
Thank you so much.
Okay, about myself. Can you hear me? I think my internet connection is not the best, but yeah. Okay, myself. Yeah, right now I'm teaching at the Gemeinschaftsschule and in Bernhausen. So after my master's degree, I went into the Referendariat, and after that, I directly went to school to collect some practical experience, which is pretty great. Yes. So far to myself, I guess. So Laura, do you just want me to start with the presentation now about the study?
Yes, please.
Okay.
And move on quickly because we are a little late.
Okay.
Go ahead.
Okay. I try to make it short. Well, yeah, I had the pleasure to work on the topic of fostering children's intuitions with regard to information and information search with Laura and also Jonathan and Björn Meda, which was a great experience. And I will now give you a rough introduction into the study, what I actually did at school. So, can you see that? Yeah, okay. So the methodology of the study follows the suggestions to introduce the concept by means of search games based on Bruner's enactive, iconic, and symbolic principle.
Oh, excuse me, we have to explain this. The EIS is
Right.
not, yeah.
Yeah.
From Brunner, of course.
Mm-hmm. You want
And
me?
yeah. Good, you go ahead and say it.
Well, yeah, it's just hands-on to start. The principle starts with hands-on activities.
And
Before
active.
one goes into the iconic or symbolic, theoretical parts behind, the hands-on activities. And the study is based on the discovery of Nelson, as you already mentioned. And they found out that children of 8 to 11 years old do have a feeling for the relative usefulness of certain questions rather than others within the framework of sequential search tasks. And the goal was a comprehensive education intervention fostering children's competencies for encoding, decoding, and search. So it was an intervention study, and we conducted a pre-test, post-test, and follow-up test. And besides that, we also applied 3 educational games. A Guess Who game, which Jonathan already quickly introduced, the number game, which Laura at the very beginning talked about, and the monster game. The following figures just illustrates a typical proportion task. And the tests included different items, like tasks on elementary probabilistic questions, coding and decoding tasks, and also tasks dealing with goodness of the split half heuristic. And furthermore, variation of the item used to survey the understanding of the probability in PISA 2003 was used in the pre-test of our study as well. And that's just the part you can see in the figure. The task was slightly altered and supplemented with further tasks. In order to solve these problems, a rudimentary idea about relatively more or relatively less was required. And the proportion tasks mimic a standard illustration of stochastics processes, the drawing of balls out of urns. And the situational context of these tasks was artificial. However, as a first step towards probability, the work with proportions is fundamental. And the items of the pre, post, and follow-up tests were equivalent as far as subject-specific contents and requirements were concerned, and the structure, the order, and cover stories of the items were different. This was to ensure that students did not perform better just by remembering what they had previously done. And the structure equivalence of the proportion tasks in the 3 tests ensured a comparability, and a similar task formats prevented a learning effect that arises while completing the tests. And the pre-test only included actually the proportion tasks. And furthermore, the coding and the decoding section was not part of the control group post and follow-up tests. What else? Yeah, the statistical evaluation mainly actually included the 3 tests because their evaluation enabled to detect, possibly confirm a positive effect of the intervention. And as I already said, besides the 3 tests, we applied the different educational games. So here you have a rough overview how we worked. So I started with the pre-test, and afterwards, a week later, I started with the intervention. And the aim of the interventions actually was to implicitly foster intuitions of information theory, information search, coding, and decoding, as well as an intuition for transferring strategies from one environment to another. So, who took part? there were in total 18 classes, and the different classes were divided into 12 experimental groups, 5 of which were 5th graders and 7 groups were 4th graders. And additionally, there were also 6 control groups, 4 of which were 5th graders and 2 were 4th graders. And after the 3 interventions, the pupils had to take a post-test. And after the time period of 3 months, pupils participated in the follow-up test that included similar tasks as the pre and post-test, with the help of which possible long-term effects should be determined. So, yeah. A week after the pre-test, the first intervention took place, and it involved the playing strategic version of the Guess Who game, as Jonathan already mentioned it. So I won't go deeper into the questions. So that each child received actually a worksheet divided into 2 parts, and one part depicting the 24 cartoon-like faces, which differed in the distribution of features. And the other part consisted of lines for children to first justify the selection of their first binary questions and how or why they chose it. And third, they had to describe how they chose the ensuing questions. And finally, they were also supposed to evaluate whether their questions had been useful or not. So was it a good question or not a good question? Moreover, each team got a shuffled deck of cards reproducing the faces of the game, from which they had randomly draw a target face. And each pair had to identify the target face of the opposing pair by asking a few yes/no questions as possible. And in order to be fully concentrate on the game and the questions, every team had to determine a player and a transcript writer. So the transcript writer was responsible for the notation of the player's justifications and answers. And after the first play round, player and transcript writer changed roles. Additionally, every team got a little box with 10 candy bars. So the teams were supposed to use the candy bars as gaming pieces. And every time a question was answered with no, the question team had to hand over 1 candy bar to the opposing team and vice versa. And if the answer was yes, nothing happened. The exchange of the candy bar or candy bars actually motivated the children, while competitive character of the game provided additional incentive. This was pretty interesting to observe. And after a few play rounds, we discussed all together whether they were good, so high information gain, and bad, low information gain questions. And we also talked about questions people had asked during the games and whether they had been useful. Whereas the control group then underwent the regular instructions in the next step, so like they had instructions in geometry or arithmetics by the responsible teacher. The experimental group was first introduced to the number game, and later they were introduced on how to encode and decode numbers according to a specific search strategy during the second intervention. So this is pretty much what Laura already mentioned at the beginning, the number game. So we started the second intervention with a short review of the last session. So we talked again about the Guess Who game. And afterwards, I randomly chose a number between 1 and 8. I would now just skip that because Laura already mentioned how it works. So you ask as few binary yes/no questions as possible. And yes, I think that should be clear. And after playing a few rounds, the students were then introduced to the so-called upper half strategy. And this was shown on the overhead projector. And I explained it by illustrating how the upper half strategy in the number game always leads to identifying the true target number with three questions in this case. Oh, I think now that was.
So, yeah, we want to see briefly those encodings. Yes.
So
Briefly.
yes, this is pretty much an example how the kids encoded or decoded then the numbers. So let's think. Yeah, so the children were introduced into the method of encoding with the help of green and red Tinker cubes. And that means they learned that each yes answer is encoded with a green cube and each no answer is encoded with a red cube. And the cube are assembled from the bottom to the top in the same order as the question sequences, so that a Tinker Tower is obtained. As you can see, there's an example of a Tinker Tower for the number 2. And the third game, which was the most interesting game and the most complex of all three, was the monster game. And the monsters were invented of researchers of the Max Planck Institute. And yeah, it was developed as a counterexample. So the monster stimuli, were a counterexample to the assumption that the split half strategy is optimal. In fact, split half strategy is only a boundedly rational heuristic because not all the 50-50 questions are optimal. And in other words, in the set of monster stimuli, as you can see in the figure, the split half, so the upper half strategy, and the stepwise information gain are not the best method when searching for the optimal question tree. So, which means optimal is the shortest expected path length. And the split half heuristic implements stepwise information gain, reducing the Shannon entropy maximally during the next step. So there were different environments, K1 to K4 and E1 to E4. And the K environments identified the split half heuristic as optimal, and the E environments, the split half strategy as suboptimal for finding the most useful first questions.
Heike, I hate to hurry up.
I know.
But we have to, because there are others who are going to talk as well.
Okay, so I make a quick shortcut. So at first, I talked with the students about the monsters, what they could see and in which ways they differ from each other. And then we pretty much played the same game structure as the Guess Who game. I would just then quickly come to the conclusion what we find out. Or rather, well, the students after the monster game, that is maybe also interesting, had to justify their answers or their questions. So why did they ask, for example, does the monster have a pink belly, or is it a pointy, or has it got a pointy horn or whatever? So they had to always justify their decisions.
They had to extract the cues. So
Yes.
What are the cues that differentiate these monsters? They
Yes.
had to recognize these cues and ask questions accordingly to the distributions.
Mm-hmm. Yeah. Right. And we also, so we also talked about it afterwards and discussed what were good or bad questions. And that was pretty much it. And yeah, I think it's clear. So a week later, then we did the post test, and 3 months later, we did the follow-up test. And to quickly come to an end, the results showed, besides the work with each class, the test results of the monster game showed that the generalization of the contents of the preceding games and explanations was not as successful as expected. And as I compared the different test results, so post and follow-up test, it occurred that on the whole, pupils showed an improvement in terms of how they asked for certain features, but they were not able to make a transfer. For example, they were not able to adopt the upper half strategy in the monster game. Rather, the aim was to see if they realized that the upper half strategy is not always the optimal solution. And the impression arose that pupils were not yet ready to make the transfer, even though the experimental group showed adequate results and thoughts during the third unit, so the introduction of the monster game. And neither the control group nor the experimental group, and it showed satisfying results in the post or follow-up test. And optimal in this context means, to identify the shortest expected path lengths of the question tree. And it also didn't make a difference if it was a fourth or fifth grader. Yes, so
That's
that
it.
would be it from my side. I hope it was quick and it was fast and it was short. So
Thank you. It was great, Heike, and we here now.
Yeah, thank you for the introduction and thank you for the opportunity to give this talk. And thanks to everyone for your energy and time on a Sunday. So I'm Lara Bertram, and I'm a PhD student. I'm Jonathan's PhD student at the University of Surrey. And I will talk today about bounded rationality in probabilistic thinking and learning. And I will focus on the role of emotions and uncertainty appraisals in probabilistic thinking. And I hope that throughout this talk, I will make clear what I mean by that and why I think that these two psychological factors are actually important. So just something maybe from everyday life. So we are all surrounded by probabilities. We all have to deal with probabilities when we make decisions, and we're all human beings. And as human beings, we're all a little bit different. We may share some general features, our cognitive systems, maybe to a large extent similar when we process information, but there are also differences. And maybe these differences are psychologically interesting. Some of us are even very extreme individuals and ignore probabilities altogether, but there are also, especially at the moment, larger groups of people who seem to exhibit something that I may just call subjective probabilities. And that's why I'm interested in how people perceive and process probabilities and how these mathematical cognitive processes are affected by maybe our personality, but maybe also our emotions, our emotional state and trait. And I would like to make a little experiment with you. You can just do it in your head. No need to exhibit your estimates to all the others, but just do it in your head. So you have this urn, and it contains 90 blue and 10 yellow marbles. And now just try to estimate how likely it would be to draw 3 blue marbles with replacement. And now try to estimate how likely it is to draw 2 blue and 1 yellow, 1 blue, 2 yellow, and 3 yellow marbles. Just try to do it in your head, really quick. And I also did this with 160 participants at the beginning of Corona, because I was interested in how well people actually do when they assess probabilities. And it turns out that for the most likely combination, blue, 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 people did relatively well. But the smaller the probability, the worse people did. So they overestimated the probability of drawing yellow, 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 largely. So everyone overestimated yellow, 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 but some people were really doing well on blue, blue, blue. And this result just hints to the fact that maybe we're not really good at estimating probabilities. And the point I want to make is that education is actually the way to improve our probability assessments, or the correctness of our probability assessments. And well, I'm not only interested in how people assess probabilities, but how we can improve how people assess probabilities. And more specifically, I'm interested in game-based learning about probabilities. And luckily, Jonathan did all the work already on introducing some games that teach mathematics, that teach probabilities, that teach about concepts of entropy. So I can focus on maybe the psychological side of things here now. What are the psychological benefits of game-based learning compared to maybe more standard, more frontal instructional ways of teaching probabilities? Well, one large factor is motivation. So if you play a game, that might be more motivating than just opening your textbook and reading. Also, the emotional component. Academic emotions are extremely important in determining performance and learning success of students. And if you can foster positive emotions in a game, for example, by reward structure, for example, by interactive game components that also have like a social game character, that would also benefit learning. And students can actively explore environments in games. So these are the psychological reasons that are pro-arguments for game-based learning, but the scientific evidence is actually quite mixed. So there are some studies showing large effect sizes for game-based learning versus standard learning methods, but there are also some studies which show no effect. And I think, like, after having conducted a very, very broad literature research, that one big reason for that could be that there are so many different methodological approaches and so many different pre-post-test measures. There are some studies that look at psychological factors, others that just look at performance. So that might be a reason for the large variance in results we find in this literature. And in a recent paper, I highlighted the need for randomly controlled trials with randomization on a subject level, not just one class doing this, the other doing that, but actually within classes randomizing the condition assignment of students. Then standardizing research methods, for example, having standardized pre and post-test time scale, but also interdisciplinary projects, just as the one with Heike Knauber, where you have teachers and scientists working together to develop meaningful studies and meaningful interventions, but also advanced technology. And Jonathan already pointed out that we're working on ways to enhance our technology, maybe even coming up with adaptive games that pay attention to students' emotions, but also their level of knowledge, for example. Mm-hmm. And we already conducted pilot studies, and we already collected more data, which is not evaluated yet, but will be evaluated in schools. And we played Entropy Mastermind with students in schools. First, we conducted a pre-test 1 week prior to the intervention. And the pre-test consisted of scales from PISA and TIMSS, so both large-scale educational studies, and questionnaires on emotions, academic emotions, and also probability and entropy questions, like this one: which coach would be harder to play mastermind with? And I hope you still remember from Jonathan's talk what this question was about determining how heuristically people assess, so which kind of entropy order parameter your estimate of this question hints at. Now hanging, but you still remember from Jonathan's talk. Okay, then one group of students played Mastermind with varying game environments. So between rounds of the game, we varied the entropy of the probability distribution the code was drawn from. And we expected and hoped that students get access to or experience different entropy levels as different difficulties of the game. And the other group of students played the Spiel dieses Risikos, and Laura will be very happy about this. And yeah, we randomized on the student level, and then we had a post-test with similar items as in the pre-test. And as I said, we have some data from pilot studies and from, so both in elementary school and at university level. And I have to say, like for the elementary school data, I'm a bit careful because it's just very few students and we had some technical difficulties. So it's also a bit noisy data. But what I find a really interesting effect is, so first of all, we didn't find significant effects on like probability questions and entropy questions from pre to post test, but this may also be due to difficulties we had. But I looked at the change in motivation and emotions, and I find this very interesting effect of, so students decrease in anxiety through gameplay. So before playing the game, they're more anxious than after playing the game. And the reduction of anxiety is strongly related to how anxious students were before the intervention. And then we also see that females, like for females, this effect is stronger. And so why I present this effect is that it's an effect that has already been shown in other literature. So I'm more confident here that I'm not presenting bogus. But yeah, so I think this hints to an interesting finding that maybe students with more anxiety maybe profit more from a game that tries to convey complex mathematical ideas like entropy. We also see that there is a relationship between how well students do on these probability or entropy questions and how well they are at playing the game. So those students not doing so well on the entropy questions are also those who don't ask very good questions in the game. And why I present this finding in particular is that I think it's good to be aware of the problem that maybe students not doing so well on not knowing so much about probabilities and entropy may also not profit so much from a difficult game because they're not, because they can't deal with a very hard game environment, then they experience that the questions they ask don't lead them to cracking the code. So from that, we actually derived our idea of adaptive games that adapt to the level of entropy or probability knowledge and give students a game with which they can actually ask good questions more easily. Yeah. Okay, so where are we in the project? The data collection is ongoing, and we're also extending data collection to other age groups. And we have international collaborations also with Cyprus and the UK. And as I said, we work on game adaptivity and we test different levels of adaptivity. One level would be performance. So we look at how well students do on a pre-test and also in the game, and then adapt the difficulty level, or also emotions. So looking at like how, for example, how motivated is a student, how bored is a student, and then adapting the level of difficulty in the game. Yeah. Laura, do I still have some minutes to?
No, I'm sorry. I'm very sorry to have to stop you all.
No problem.
We have a couple of words, that's fine, because we have to move on. So there's still some other brief things and people I want to talk about.
Yeah, no problem.
No problem?
Maybe just then I would like to, that might be a fun last slide, because I showed you a very similar slide earlier when I showed you how people deviate from the true probabilities. What I find in current data, and again, this is data from the beginning of the COVID-19 pandemic, where I also asked people, well, how anxious are you actually right now, given that we have this pandemic. And I see an interaction of people's anxiety and also of their uncertainty with how well they're doing on these probability questions. So I'm happy to share these slides if you want to have a closer look at the data or the plots I have. But for now, I don't want to torture Laura.
You're not torturing me.
I am a little bit, but maybe a summary, okay?
Thanks.
So maybe a summary. First, very important. Ooh. Okay, that was my computer. That was a bug. We need effective and educational interventions to teach probabilities or to teach probabilistic thinking, but we also have to evaluate them rigorously. Academic emotions, but also emotions in general, play a role in probabilistic thinking and also in the ability to make good queries. And yeah, I mean, we have these phenomena right now, so I think it's important to look at how people assess probabilities. And yeah, thank you for your attention and enjoy the next talk. And thank you for listening.
Elif Özel works as a teacher, and we talked about Eningen. So Lara talked about things going on in Eningen, so her intervention, her study. There is also another study based also on the mastermind game, and this was done by Elif Özel, who is now in Freiburg. So you see this, this overlaps and flows between Freiburg and Ludwigsburg, which I find very happy, very, lucky. So she's now in Freiburg and doing her PhD with Timo Leuders and Katharina Leuvel, which is a wonderful thing. So what did she do? She worked based on ideas, again, of this project that we talked about on Mastermind, yet on a very concrete and active way of doing Mastermind, namely with urns. Move on. Okay, so look at this urn. You see the title of her work, and there is a submission already. Playing Entropy Mastermind can foster children's information theoretical intuitions. So you look at this urn, this jar, and it contains some cubes. And the question is, if I pick one at random, how would you ask questions to, what question tree would you use in order to find out what color the cube is that I have in my hand? I don't want to go through these trees of questions, but these are possible ways of doing it. If the jar looks like this, as we see, we know this is equally distributed among the colors, so entropy is maximal. So you have also a way of solving this, which is pretty canonical. And Elif worked a lot with these jars and with working sheets that you see here. Again, the question was whether children got the intuition that the difficulty in question asking, in choosing good questions, depend on the composition of the jar, and that some jars are more difficult than others because entropy is growing. So we know the most difficult is if all colors are equally distributed. So she worked playing the game and, letting them guess the codes, and then also preparing jars. So there were two activities at least: children preparing jars, children guessing codes, and in the end, there was, of course, a test. There was a pre-test, which was just based on proportion comparison. So she did not teach the game so that they could play and be tested already in the pre-test. We avoided that. They were tested in proportions quite similar to what Heike Knauber did. Proportion comparison, the jars, 1 against 2, 2 against 5, which urn is more, is more convenient if you want the color blue or whatever. So 1 against 2, 2 against 5. Suppose you have to guess which is more convenient. Fine, these kind of questions were asked in the pre-test, whereas in the post-test she asked directly also not only proportions, but also questions directly connected with what she had done, the intervention. And the conclusions you can see here. This is very, very short on purpose because we are at the end, basically, of our unit here. We underestimate the competencies of children for mathematical concepts. Fine, this is simple. And what she discovered is that most children were able to compare jars, although they don't have fractions and although they don't have all that mathematics, they can compare simple proportions, and they are based on their intuitions and their experiences from the game. And of course, they discovered that the difficulty of guessing the code varies with the entropy of the code jar, and they definitely developed what we can call entropy intuitions. Fun. The best part is, of course, that children had a lot of fun and asked several times when they were going to play Mastermind again. So this is a very short intervention now, and you see, this is the story about entropy and information. In these stories, of course, proportions are a very important factor, proportion comparison, but we have done other studies. In fact, another direction of studies is all concerned with risk literacy. And here again, a book. People write so many books. This is another book. And this book was written with Ulrich Hofrage, yet one more book. And the book was based on results by other students. Maybe we can ask Christoph Till to shortly introduce himself. Christoph? If he's not disappear. Sí, eso se acabó. Christoph, yeah. Let's go shortly. Is Christoph Till still there? Or did he disappear? Oh, he disappeared. All right. So some of the discoveries on what children can achieve in risk literacy were performed by Christoph Till, who was here and now is not. And what he did, you know, there are many aspects of risk. If I tell a child in 4th class, look, your Taschengeld, your week money, is 5 euros, okay? Now I propose to you that we throw a coin every week, the mother says, and if it turns up heads, you get 20 euros, but if it turns up tails, you get 0. Okay, so he compared. He did this with many, many children. We had done also experiments on this in Rico-Stadt, which was a project we had done before, and he found out interesting things. For instance, you know, that there are differences in risk proneness. And other studies that we have done in several instances have proven that girls, what would you guess, Elizabeth? Who would go for the bet and who would rather stay with those 5 euros instead of perhaps losing them? There is a risk. Excuse me? The two groups were boys and girls in a 4th class. So the 2 groups are boys and girls. Yes, boys like risk more. And this is about, you know, human history. We are very grateful that boys like risk more, but we are also very grateful that women are risikoscheu, less risk prone. And I think that this has also, in the time of COVID, if we compare different countries, you know, it's been done a lot, those countries governed by women, you know, use the best policies. This is the truth. Perhaps because they are less risk prone. So in some cases, it is a very good thing. And Lehman Brothers wouldn't have gone astray if it had been Lehman Sisters. It was a joke. Okay, so that was one story, you know, risk. And of course, we did many games. We used Mensch ärgere dich nicht, the Ludo game, and several positions, so they had to compare and decide what they would do in such a position. So that was work we had done, and Christoph Till also trained his children as fourth-class children in conditional probabilities using cubes. You see the cubes that also Heike Knauber used for coding, we use for encoding girls and boys, long hair and short hair. You know, in this class, if I tell you that I have seen a child and has short hair, would you bet it is a boy? So it is the sensitivity, you know, all those stories, diagnosticity, sensitivity, we have done a lot in fourth class already. And we have had very good experiences and published results, not only in Frontiers, but there is a paper in Frontiers in 2020 by Ute Sprösser and Christoph Till, based on work that was done before. Very beautiful paper describing this sort of experience. Okay, so, and also you can read this very beautiful book with a nice cover. I don't know what you think of this cover. When I was showing this cover to Colombians, Francisco Vargas said, "Oh, that girl is so rich. You know, she has nice clothes in the Swiss landscape. It's not a Colombian landscape, you know, the average one." So yes, this was commented on this cover. Well, covers are important. The title is Wer wagt Gewinn and wie Sie die Risikokompetenz von Kindern und Jugendlichen fördern können. And just to show you the very last thing, what time is it? Yeah. Please open the web page that we talk about a lot in that. Okay? So I have to share the web page. Some people don't like breast cancer. I belong to those. Some people don't like the mammography task. So Jan Multmeier, someone who wrote a PhD thesis in Berlin, you know, the Max Planck Institute, he had the good idea to replace those very scary topics like breast cancer by mermaids and princesses. So here the disease is being a princess, and the symptom or test is wearing a crown. So you can work with this. For instance, you can group crowns together. This is a very first statistical activity. Now, if I tell you you're a child and I tell you that I saw one of these creatures on the street, the child immediately say, mermaids don't go on the street. Fine, okay, so I met one of those and was wearing a crown. Would you bet that was a princess? Okay, questions like this. And you, in this page, which is very well described in the book, you can vary many things. You can vary the population, you can vary the base rate of the disease, which is being a princess. Then you can go to construct a tree quickly. Okay, the double tree we talked about. And you see in this double tree, you have a lot of good things. It's not quite as good as the net. Do you like me? That I say it is not quite as good, but it's pretty good because you can do conjunctions here, princesses with crowns. You have two directions. So you have fairy folk, and then you have princesses and mermaids. So this is the causal direction for wearing a crown. If you're a princess, you wear a crown. And you also have the diagnostic direction from bottom to top. Namely, you start with this symptom, the crown or not crown, and then you go and see whether wearing a crown is diagnostic for being a princess. And then you have options. Why do we have options? Because it can get you the levels, for instance. We can vary levels. So in the very first, remember the discussion we had about what is natural frequencies. I don't want to enter that question now because I think Ulrich Hofrage is among the people there. So I don't want to enter that discussion. But with these levels, you can vary things and make it more and more closely to what you want to have in a probabilistic setting. For instance, here you are varying, you can vary these, yeah, you can vary the base rate and express it as percentage. You can vary, okay, sensitivity, okay. And now you can go to level 3. And level 3 implies a sampling. So you're resampling from a population each time. And you can go now to the icon array and show it and resample. Maybe we do a little bit more fairy folks. Yes. And you can do resample. Okay. Resample again and again from a population. Okay, so these are 3 levels which are important for understanding these concepts. And now we go to the risk, and we go back to the main page. Okay, we're changing the risk. We can show perhaps bike accidents and helmets. Maybe, okay, you know, if you are wearing a helmet, there is a risk reduction if you fall of breaking your head. And this is important. So group helmets together. Okay, and now you can compare. You see the risk reduction here. Leave it without, yeah, the risk reduction. You can compute that risk reduction if you're wearing a helmet of not, you see, spoiling your head means having a pad in your face. So you can compute that reduction, and you can see the 2 grids close to each other. You can, again, vary things here, vary the number of accidents. And here again, you have options, and you can do a tree. You see, in the tree, you can also express this risk reduction. Yeah? You can go and find the nodes and look at this tree and see the risk reduction.
The link.
Okay.
In the chat.
Thank you. And now we go to the last topic that we want to briefly mention, the conjunction. You see, we talked yesterday about Karim talked about seeing conjunctions. There is a lot of work on the conjunction fallacy, and we also had a master's student working on conjunctions. Let's look at football and chess. Yes? No, let's look at the 25 ones. Okay? Okay, so the question is here that you want children to understand conjunction. You can decide how many children here and which children do soccer. So place a ball on all those you think. No, it doesn't stick. Use this one. Yeah. Okay. Yeah. Yes. Okay. So children think that if these are boys, most of them like football, and then some like chess. Not too many. And some of them like both football and chess. So you can go to story 1. Mikkel loves Sudoku and mathematics. He does lots of puzzles, and he has memorized pi up to 50 places. Imagine 100 boys like Mikkel. Are there more boys who are good at soccer, or more boys that are good at soccer and chess? So those who know the conjunction fallacy know that this is exactly the topic. And if children have been trained with those icon arrays, they don't commit the conjunction fallacy. Story 2. Mikkel loves Sudoku. This is a little more subtle. He does lots of puzzles, blah, blah, blah. What would you bet? So now you express the question not with how many of how many, but what would you bet that Mikkel is good at soccer or that Mikkel is good at soccer and chess? And again, using these grids and icon arrays has helped a lot to have children, be free of the conjunction fallacy. Okay. Here again, you could change many parameters. I don't want to go through that. There is a link to the page. And with this, I would like to finish our activity today. Can you introduce them?
So, dear colleagues, we're all very exhausted after a long day, and I promise I will not exhaust you more, but entertain a little. The task for me was to do something entertaining, which is from my business as a mathematician, as a education researcher, and as a magician, maybe. It's a mini talk with mini music and will not last too long. I'm very sure you don't know what I show because it's not yet very, very popular, but will be, of course. The context of my presentation of 3 little pieces is the connection between music, mathematics, and psychology. And as Hector already showed us yesterday, there's a strong connection. It's all about repetition, variation, randomness. And as a physicist, I would say it's all about symmetry and symmetry breaking. Let's not go too far into it. But what would a mathematician say about this connection? He would say mathematics is so universal. It's the foundation of everything, of how the brain works, how music works. So no, of course it's connected. What was a psychologist say? He would say, of course, the brain creates music, the brain creates math, and so it's no wonder it's very similar. And what would a musician say? He would say, who cares? Let's do some music. And that's what I'm going to do. So the big question is, how does all this relate to each other? And I'm only going into the very, very simple question, can we go from mathematics to music in a way? The other way around, you know, you can analyze Bach music by mathematics, but can you create music by using mathematics? And I will show this with 3 short pieces, and 2 of them are by the not yet very famous Tom Johnson, American composer situated in Paris for a long time, and he created lots of pieces of music to show how mathematics can be the core, the generating cell for music. And one of them is a multiplication table. Math educators begin to expect interesting things. The multiplication table somehow shows how mathematics and music are not so related. You should now see the multiplication table. And the story behind it is people always say that 2 times 3 is 6, of course, and that 3 times 2 also is 6. But while in mathematics it's the same, in music it's totally different. And of course, 1 times 6 is totally different from 6 times 1. So math is completely different, and it's a wonder how mathematicians have got through all these centuries in telling it's the same. This is the story, and the piece of music behind is simply playing all these pieces one after the other. The multiplication table as music, something sounds like this. Let's try. I'm going to play on the piano and when the computer stops finally. So it's 1 times 1, 1 times 2, 1 times 3, 1 times 4, 1 times 5, 2 times 1, sorry, 2 times 2, 2 times 3, 2 times 4, 2 times 5, 3 times 1, 3 times 2, and so on. I spare you the rest, but you may ask yourself, what would it be like hearing the whole multiplication table one after the other in a concert? And it's some say it's music, some say it's nonsense. It's your choice. Anyways, it's kind of artistic experience to go through it and feel how the rhythm, how the patterns work. Somehow, although math is different from music, math creates kind of music. Of course, in this way, maybe not a great piece of music. But I will show you a second piece of music of Tom Johnson where we maybe discuss that this is a little more convincing. So I stop sharing this screen, go back. And this second piece, Tom Johnson, is Narayana's cows. And you will find the idea in this piece that, as Tom Johnson says, he does not want to create music, to compose music, but to find music. Let's see if he succeeds. Narayana's cows is a simple story. Narayana was an Indian mathematician in the 14th century who proposed the following problem. A cow produces one calf every year. Beginning in its 4th year, each calf produces one calf at the beginning of each year. How many cows are there altogether after, for example, 17 years? So you can work on it, or you can listen to what I'm going to play. When I just demonstrate what the piece is constructed like again. So first cow with first calf. First cow with 2 calves. Cow with 3 calves. The first calf has become a cow, and him or herself produces a new calf from the next generation, sounding like. When the first and the second calf have become cows producing themselves calves, sounds like. And so on. So you see, it becomes a little more complicated, a little more intricate, a little more interesting. When you go into it mathematically, you can count, you can add, you can ask yourself, what will the sound be like? Maybe you will discover that you know this somewhere. It's very similar to the rabbits, to the famous rabbit problem. And you can even calculate very interesting numbers. It's a golden ratio for cows instead of rabbits. But you can also say, no, let's do it musically. Let's skip the math and try, what does it look like, hear like, listen to, can be listened to when it sounds like music. And I'm going to play this to you, but don't worry. I'm not going through the whole piece. It lasts about 15 minutes. And it's really an experience. If you like, just Google Narayana's cows, will find many different interpretations. You have to now listen to mine in a very short part of it, just to get the feeling what mathematics is listened to. Here's like. So this is Narayana's cows, short excerpt played by me. So on. I can listen to it all day long. Maybe you can, but you have to decide for yourself. This is my question to you. Yeah, you may count yourself, or you may find out how the calculation goes and spare the details. Okay, this is a piece I've presented many times, and it's in between inspiring and exhausting, and I've promised you not to exhaust you. And therefore, as a last piece, the last demonstration of the connection between mathematics and music, I present you a piece of music that I composed. Sorry, I didn't compose it, but just as Tom Johnson says, I found it. A piece of music I really found. It was there. I did very, very few things. I programmed a little and counted a little, but this is music, nature, or God, as you choose, composed and gave to us. It's the prime numbers. I will now present you how prime numbers sound like, with doing very, very little except for somehow arranging them a little, yeah? And this composition, you can see I put some of them on YouTube. I have not yet become so viral, as you can see, 146 in 5 years. So please give it to others. Please click a lot for making me famous, or just get help. So last piece for today. It's Prime Songs by not me. Yeah. I will play prime song number 1, which is simply give a tone whenever a prime occurs, and it sounds something like this. You see? Can see the numbers in it. You can run this piece in the background in the kitchen and listen for it all day long, and ask yourself, what would it be like in 2 hours? Will it be similar or not? Or you ask mathematically, what are the differences? What are the distances between the sounds? Will they increase or not? Will there be some pairs? Always, will you also in 2 hours listen to some pair? Actually, this is a question that even mathematicians can't prove until today. Will there be pairs, close pairs, eternally, or sometime they stop and be only in the further distance? It's an open question to mathematics, but still musically a little boring. So let's put the primes in 2 lines.
We finished.
Any question? Yeah. Let's put the primes in 2 lines. Prime song number 2 does the same, but simply puts them in a first line with a even, and in a second line with the odd numbers, and this is what the primes sound like. Let's restart. It's a little more musical, yeah? Do you hear? It's a little groove. Da 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 da. Offbeat. So still, let's move to prime song number 3, where the prime numbers are sorted in 3 lines: 1, 2, 3, 5, 4, 5, 6, and so on. And then it looks and sounds like this. It's a little interesting because you hear 2 types of intervals, up or down. Pause, up or down. And you ask yourself, is there a regular pattern? Up, down, down, up. And when you see, oh, pattern, no. Pattern? And actually, there is no pattern, or every pattern you see will recur sometime, but there will be always a new pattern. So it's a kind of listening to the structure of prime numbers and all the structures you can do mathematically. Of course, you ask, what is number 4? I dedicated this to Tom Johnson because it sounds like some of piece of Tom Johnson. Number 4. So now we have pairs, and somehow, although we have 4 tones, only 2 tones are used. What is our tone of row 2 or row 4? Of course, there are no prime numbers in row 2 or 4 because they are multiples of 4. And the rest is very similar to the experiences before, except we have intervals now. We have 2 sounding at the same time. And it's a tritone because I divided, of course, the octave in intervals. Let's proceed to number 5, which I dedicated to Philip Glass. Now we're talking. Yeah, now it's music, and you see there are lines, there are melodies, there are double melodies, it's polyphonic, it's happy, groovy, happy. I've done nothing, it's really primes. I have not put any dot anywhere. It's whoever did this. See, and there are melodies, sub-melodies, and you will find ever changing new themes and motives. And of course, after 6 comes 4, 5 comes 6. Go up. Totally different. Now only 2 tones are used because all other lines contain no prime numbers. And it's a 7th chord interval, and therefore it sounds a little aggressive, but okay, maybe 7 is better, and 7 must be better since there are no more missing lines. Now at least 2 players or 3 players are interchanging. And it's become a little band, a little jazz band with interactions, jam session. Number 8. Drama. Only 4 lines are used. Now it's more like chords, interchanging chords with different intensity. No more melody, but more rhythm. Number 9. Now the intervals have become more interesting. It's not diatonic, but chromatic. In orchestra, with pauses, intermissions. Number 9, number 10. And actually, this exactly sounds like any piece of Steve Reich. Steve Reich has composed music in the same vein, with the same kind of different instruments, but it's 100% Steve Reich. Don't worry, I'll be finished soon, but we have to close until the octave is full. And when we reach 12 and the interval has no more nice tones for us, this is 12. All tones from the chromatic line could be used, although only 4 are used. What will happen if we use an interval more than the octave has for us? Of course, we have to do microtones, and from now on, it's kind of matter of taste. Sorry, let's do this. Yeah. Yeah, and this is the finish of my presentation. If you like to have the apps to listen to it at home, please send me an email. Yes. I will really like if you go more into the music and tell me what it does to you. And for now, thank you for your attention in this long day, and thanks for being able to present this to me.